So my name is Ferras Hamad. I'm a software engineer at NumFOCUS, and I'm currently working on machine learning infrastructure. And today I was going to talk to you about reproducibility in machine learning systems. Hopefully that's okay, because that's kind of like the only talk I have prepared. So today we're going to focus on defining what we mean by reproducibility, especially in the context of machine learning systems, which no big surprise, that's the title of the talk. Why it matters, and kind of outline some real world benefits, and hopefully illustrate that through some real world examples. And then we're going to talk about how we actually addressed reproducibility at NumFOCUS. But before we get into all of that, I figured it would be helpful to have a couple of brief primers. One about machine learning at NumFOCUS. So typically, when people hear that, they think of our personalized video recommendation, which is very understandable. It's one of the, I guess, more user visible use cases, very important to us. But before a title even hits your screen, there's actually a lot happening underneath the hood, and machine learning is applied at every kind of step in the funnel. So from pre-production and production, such as helping determine the value of content, optimizing production schedules, so figuring out which actors and actresses need to be where, and the order in which sets need to be shot in, to more streaming and system use cases, such as figuring out the optimal layout of our content and our CDN caching, figuring out how to best utilize our infrastructure through job scheduling, intelligent job scheduling and preemption. In pre and post launch, trying to predict the effect of certain titles have on our churn and retention rates, figuring out the impact of our marketing. And really, there's just hundreds of different business use cases in NumFOCUS that require machine learning or depend on machine learning to some degree. But reproducibility pretty much comes up in all of them. And now let's talk about machine learning in general. So some of you may be familiar with this already. It's an infographic taken from a paper published a few years back. And it does a pretty good job of illustrating a powerful point. So what we consider, or what a lot of people think about when they think about ML, is really just that small, barely visible black box in the middle, which is the ML code. And a lot of times this is just maybe 8 lines of Keras code. But when we're talking about machine learning systems in production, you'd actually probably find yourself spending way more time on these other components data verification, compute resource management, deployment and serving infrastructure. Okay, so now we got that out of the way, we could go back to the matter at hand, which is talking about reproducibility and what that really means. And I'm sure most of you probably have some idea of what the definition of reproducibility is, and it's probably something to the effect of obtaining consistent results through repeated trials, right? It's more or less something like that. But what does that really mean in the context of machine learning? So let's kind of just take a step back, start with a blank slate, and figure out what components we need to have a reproducible ML system, right? So one, you probably need the model, right? Helps to start there. You could get your prediction inference results, but you can't really do much after that. You might need to, if you want to deploy it to a different execution environment, you might need to recompile it. If you want to build on it, you might need to look at the code. You might need to understand how it works. So helpful also to have the code. And you all might be better than me, but usually it takes me a few iterations on the model before I deploy it to production. So you probably need some kind of versioning, right? But no, this is that new. We've had version control in software engineering for 40 years. But that's really still not enough to create a fully reproducible machine learning system, right? To fully reproduce training, for example, you need the hyperparameters and associated metadata of the model. You'd also need the libraries, so which version of TensorFlow you're using. So now we're talking about dependency management. which is a pretty hairy problem, especially when you talk about dependencies and transitive dependencies. And that's still very difficult, right? Even in traditional software engineering, let alone machine learning. But again, still not enough. You probably need the data, right? You need the training, test, validation data to produce the same model. But again, there's still more, right? There's a lot of inherent randomness in many machine learning systems, like what random weights did you start with, what seeds did you start with, and really maybe even environmental factors, right? Your data center got hit by a solar flare, flipped some bits. Really hard to kind of capture and reproduce, so we'll just call that entropy, right? So to say your system is fully reproducible, you kind of need to provide all these components, right? And we, I guess, typically talk about reproducibility as a binary construct. So either something is reproducible or it's not. But especially in the context of machine learning, it's really more helpful to think of it as a spectrum, right? So you start all the way on the left from not reproducible or minimally reproducible to kind of like the holy grail where you're able to reproduce everything down to the bit. And as you move up kind of the step ladder, you unlock, more and more practical features. Which kind of brings us to our next topic, which is why reproducibility matters, right? So I know a lot of you probably have some sort of science background, and like since grade school, you've kind of been drilled that real science needs to have reproducibility, you need to get the same results. But kind of like what benefits do you get like from like a business use case, for example? So the best way to really illustrate that is to just kind of go over some real world examples or real world like examples. So let's say you're a data scientist, right? Which for a lot of you, that's probably true. So not too big of a leap in terms of imagination. So, you're working on this project, very successful, great job, promotions all the way. You move on to your next project. But, after a few months, you need to go back either to retrain something you've already deployed, or the business use case has changed, so you need to modify your model. No problem. You follow best practices. You have your code in GitHub. You pull it down. You're like, I just need to make 2 lines of changes. I'm good to go. But then it doesn't really work, right? So it turns out that there was a lot of dependency drift, right? So you find yourself in kind of dependency management hell for 2 weeks until you get out. But now, smooth sailing, right? And you figure out that, I'm going to run my flow every day so this doesn't happen to me again. Use kind of like job scheduling framework or, just plain cron tab. But you still run into issues. You get these transient errors. You can't figure it out. You get these unintelligible error messages. You escalate to an engineer. Engineer might not be able to reproduce. He might not even, or the engineer might not even know how to run your flow or training. Maybe they're just drinking coffee, so it just takes like a while to get back, right? So you burn a few days there. It turns out that the PyArrow version you're using in production is old and different than the one you're using locally. That's why you can reproduce the issue locally. And the version in prod doesn't handle certain data types correctly. But you get that resolved. Again, smooth sailing. But then you hit another issue. Well, not really an issue, but you're so successful that they decide to expand the scope of your project, and they add another data scientist to help you out. And data scientist is excited, ready to make some impact. So naturally, the first thing the person does is pull down the project, try to replicate what is already running in production, but unable to get it working. Dependencies are off, configurations off. So you spend kind of a week kind of helping get your coworker up to speed. So again, right now you're wasting a lot of time. It's been like around 3 weeks. burnt, and now you enter kind of like the development phase, right, on your newly expanded scope. And especially early on, it's very typical to like experiment on a lot of different dimensions, right? You're changing kind of what features you're using, hyperparameters, model types, etc. And it's kind of very easy to lose track there. You could find yourself in a situation where you're not really sure how you got the results, like what version of the feature extraction library did you use? What version of TensorFlow were you using? What table were you reading from? So like you might end up spending a lot of mental bandwidth just trying to organize your different experiments. And in like some of the worst cases, you might end up rerunning your experiments just because you're not really sure how you got those results. So I guess kind of like what happened here? What led to this like series of unfortunate events? Like what was missing? Why did you have to spend like around a month working on, I guess, stuff that was really outside of your job description, that wasn't really core to what your job was about? So one thing is trust. The ability to depend on your system to like run indefinitely without any or minimal human intervention, and being able to trust the results that it produces, right? And like being able to take whatever you built and just run it in trust that it will be able to run in an arbitrary environment. And coming from Netflix, where we're like a cloud-first infrastructure, or based on a cloud-first infrastructure, we don't really own any of our own data centers. Pretty much everything is treated as ephemeral, so this is very important to us. Another one's debugging, right? So any engineer will tell you that 90% of like resolving an issue or bug is being able to reproduce it consistently. As soon as you do that, it's just kind of a matter of time before you're able to deploy, fix, or resolve the issue. And for the non-engineers in the room, I'm sure you've all faced the frustration of some engineer just closing a ticket as can't reproduce. It's not that the engineer is lazy. I mean, like they could be lazy, but it's also sometimes impossible to, or like very difficult to reproduce an issue with incomplete information. Collaboration, right? Allowing multiple people to work on the same data science projects. I know a lot of like data scientists are kind of lone wolves, but for some projects, there's like several, like a team of several data scientists working on it. And also like removing the fear factor, right? A lot of times people are scared to jump in on like a new project, because they're worried about breaking something, right? So if you're able to give them the ability to take whatever's running in production, run it locally, run in a dev environment or some sort of safe environment where they could just kind of play around and get their feet wet, that'll really improve in terms of collaboration. Rapid prototyping. So the ability to iterate quickly without spending too much mental bandwidth, keeping track of the mundane. And these are all the practical benefits, or all these practical benefits come from having a more reproducible system. So that's kind of why it matters. So if we kind of go back to earlier and take the infographic from the beginning of the slideshow and discuss and like the different components that we talked about, and we create like a ML system stack. Towards the top, you'll see model training, feature engineering, etc. And as you go deeper, you see stuff like job scheduling, compute resource management, data warehouse management. And as you move down the stack, it becomes less relevant to data scientists, right? For example, I've never kind of had a conversation with a data scientist who cared about whether his model training ran on a compute cluster using Kubernetes and Mesos, right? I've never had that conversation. Similarly, from like an infrastructure point of view, the higher up you go in the stack, the less like software engineers and data engineers might care. Like most infrastructure engineers would not care how you handle your categorical data, for example. So now is probably a good time to segue to how we handled reproducibility at Netflix. So the way we addressed it is with this Pythonic framework developed internally called Metaflow, and it was developed for data science projects. So I'm only going to give a kind of high-level overview of what Metaflow is. There's already other talks online specifically devoted to Metaflow, and before I upload the slides, I'll make sure to link you to those. Much better speakers than me, so you should probably listen to those. So Metaflow provides a lot of features, but I'm only going to dive into the ones that are most relevant to reproducibility. But at a high level, Metaflow is really just meant to kind of package the entire machine learning stack and provide a more human-friendly interface so data scientists could focus more towards the top of the stack, model training, feature engineering, and not worry about everything below. And infrastructure engineers could focus on providing paved paths and stabilities to the other components and focus on, creating more leverage to support a much larger org. So just to give you like a feel of how a Metaflow project looks like, it's really just based off like a DAG execution flow. So you have, you define what's called a flow. Each instance or run of a flow or iteration of a flow is called a run. A run is made up of many steps. So start, A, B, join, and end are all distinct steps. And each step could be one or more tasks. So on the right, you'll see the associated code. It's pretty simple, just pure Python. Any function that's a step needs the add step decorator. Not too shocking there in terms of naming. And everything else is just regular Python code. So not much magic. This is an example of a for each. So the overall structure of the DAG needs to be static, at least for now. But you can have some parts could be dynamic, which is the size of the for each split in this case. Here it's 3, but it can be dynamic. And it's another example of, or it's one example where one step contains many tasks. So in this case, step A is made up of 3 tasks. So let's jump into some of the features that Metaflow provides that are relevant to reproducibility. So one is code packaging. So we talked about how we need to have version code to be able to have a reproducible system. So what Metaflow does is it takes your code, your execution environment, and your working directory, packages it all up, pushes it to S3, and this is done for every run and iteration, so it's all versions, and can be accessed later. Metaflow also provides dependency management. Every task is actually in its own isolated runtime environment. So you could do something like this, where you have step A and step B, and each of them actually use conflicting versions of the same library. And again, this could be done because they're actually in separate environments. In some cases, they're not even running on the same machine. And as you can see, we use Conda here for dependency management. We did consider a few other alternatives. You could use pip, but it doesn't really provide runtime isolation on its own. It's not language agnostic. It's very specific to Python. But it is low overhead. There's Docker, which does provide runtime isolation, is language agnostic, but I really wouldn't call it low overhead, especially if you're not coming from an engineering background. Can get kind of complex, kind of intimidating, and technically you'd still need to use pip or something like that to install the packages when you're baking the image. Also, in terms of iteration speed, it's kind of on the slower end if you need to rebuild the image every time. And we felt Conda kind of provided us the best of both worlds there. Metadata persistence. So Metaflow does does provide some sort of metadata persistence baked in. It automatically persists in versions all instance variables as what we call artifacts. So in this example, we have self.df, and you could just think of that as a pandas data frame or something like that. And that's defined in start. but we could still access it and end, even though it's a separate execution environment. So all of these are made accessible in subsequent steps. And these artifacts are also accessible from other flows and can be loaded using a client API. So you can even pull them down into a notebook if you want to do some analysis, share results, etc. And the way we do that is pretty simple, probably not too surprising. You take the pandas data frame, you serialize it using pickle, something like that. So you get some bytes. We compress the bytes. Here we do I guess kind of some standard hashing. So we hash the byte values and use that as the key. And then we put the entire payload in S3. And the reason why we do the hashing is to avoid storing duplicate data. So if your data hasn't changed and you store that large pandas data frame under multiple different names, we won't duplicate the data. So it reduces our memory footprint. But overall, with I guess the compression and the hashing, the actual cost is relatively low. The logs are also persisted in a different manner, but standard out, standard error are accessible later. Metaflow does provide some isolation. I wouldn't really call it complete by any means. Since the users running arbitrary Python code, there's really no straightforward way for us to prevent any side effects. But if two data scientists are running the same flow, we do provide some namespace isolation for the runs, metadata, and artifacts associated with them. So if Jesse pulls their latest prediction flow run, they'll get 8, whereas Tracy will get 6. So you could have potentially multiple people working on the same project without necessarily stepping on each other's toes. So going back to this diagram, where does Metaflow kind of land in the stack? So we provide, model code inversioning, metadata. We have dependency management, but we don't really persist all the data, right? So we land about here. So we don't persist everything by default. We do obviously store the artifacts, as previously mentioned. But storing all the data could be prohibitively expensive, especially if you have gigabytes or terabytes of training data. And to store that on every run, every iteration is pretty expensive. And we actually found that in most cases, you don't really need to do that, especially if you have proper data hygiene. So if you treat the underlying data as immutable, have proper partitions. So you have, for example, you have a Hive table, you can partition by date, and you just store the partition key as an artifact. That usually works out pretty well. Works out for our use cases. I'm not saying it works for all use cases. So, if you're watching this on YouTube, no need to leave hateful comments. But for the most part, it works out well. For entropy, honestly, we don't really do much here. The value, the cost-benefit analysis doesn't really work. Technically, you can store some of the noise as artifacts, like which seeds you used and what random weights you used. But, we don't really go too far there. So kind of let's revisit our example from earlier. I know season 2 is usually worse, but hopefully that is not the case here. So you could basically pick off where you left off, right? We kind of, with dependency management, you're not going to face the same issues as before. Debugging is made simpler. So everything's reproducible, and even in the case we described earlier, you probably actually wouldn't even run into the bug at all, just because you kind of have that execution environment baked in for you. When you have a new person joining the team, again, relating back to the first point, you have effortless runability. So a person could come in day 1, start being productive. And then in terms of rapid prototyping, all iterations are namespace and persisted. So you could kind of have multiple streams going at once. And the framework itself kind of keeps track of the experiments and iterations for you. So Netflix is paying me to be here, so I feel I need to put in some plugs. We are hiring. I don't know why I made the jobs link so small at the bottom, but it is what it is. So that's specifically the job link for the machine learning infrastructure team. We're looking for a couple of new colleagues to help us out. But I do encourage you to just go to jobs.netflix.com and browse all the postings. There's some great positions out there, and we'd love to have people like you. I also want to note that we are looking into open sourcing Metaflow. So if you or your organization wants to give it a try, please contact us or talk to me after this talk. And that's it. That's all I got. Actually, yeah, there's Q&A too. I forgot about that.
Hi, thank you for the great talk. This looks like a really amazing project. I'm curious how you invalidate the cache artifacts. So if your data scientist changes part of their flow code, do you invalidate all the cache artifacts or just the ones that depended on that code somehow?
Well, we'll persist it for every run, right?
Oh, so everything will be regenerated every time you run the code?
Yeah, so are you specifically talking about, let's see. Are you talking about like this slide? When we like persist the data frame?
Yes, exactly.
Yeah. So again we hash based off the bytes. So if the data didn't change, we're not going to repersist it. But if the data did change, we will repersist it.
So you're not taking advantage of the caching to speed up later runs. It's just for reproducibility.
Yeah.
Great. Thank you.
Yeah, but since you brought that up, there is a resume feature. So you could actually resume from any step from any previous run.
Does anyone have more questions?
Quick question on what is like the typical or recommended size of a task in terms of the volume of data it might process, the runtime? Is it like really small function or is it something that runs for an hour?
I guess like size is like a broad term because it could be like in terms of compute resources, memory resources, just pure number of tasks. And I guess like in terms of the framework itself, there's not too many limitations. I guess it really depends on the underlying infrastructure. Like we're plugged into Netflix's infrastructure, which is built on top of AWS. So in terms of like storage, we have S3, so it's pretty big. We don't worry too much about it. In terms of like compute resources, it is like elastic scaling, so it's super important. We could scale up, but there's associated cost with it. So it really depends what you mean by size. Yes.
More questions? Do you have questions? All right. Please thank you, Ferras, for the great talk.